Hi, everybody. It's time for us to get started. This is our 12th lecture, and there was a homework assignment that was turned in on Friday that I did not grade. So homework ones, and I will have them graded and handed back next time. Okay. So I'm sorry about that. I just chose not to. That's what happened. We have a homework assignment number 2, which you'll get a chance to rewrite, and it will be due on Friday. So there's several problems there. I want to make sure everybody has that problem set. Does anybody need that problem set? And secondly, I wanted to open up the floor to any questions you might have about the problems or anything else we've covered in class. Sean.
I do have a question. On
Yes.
number 2.
Yes.
Is it okay for us to do this problem just like if this was a problem in, say, math 10-20 or
Exactly. So problem number 2 has to do with solving 4x plus 5 inside absolute values being less than 8. And essentially for problem number 2, what I want you to do is use this fact that if you have A is less than or equal to C, in this case just less than, then that would imply that A is sandwiched in between C and minus C. And then you can use normal operations to isolate the variable x, okay? So that's why it's worth only 1 point. Essentially, I just want you to realize we're using that fact. Okay? And so that fact that we proved in the theorem that had 3 parts, this was an if and only if statement, it had less than or equal to, was something that is used in math 10-20, intermediate algebra, a lot. And so it's a true fact, we proved it, and it's useful. So that's all I'm looking for there, John. Thank you for asking. Was there anything else anybody would like to see done or ask about, whether it be from homework or the things that we've been covering? So this is problem number 2. Anything that anybody wants to ask about? Okay. Well, I'd like to progress further in our coverage about sequences. And what we want to do now is prove a fact having to do with the limits of the sequence being unique. So let me start off with this definition. And recall this definition. The sequence of real numbers let's say x of n converges if there exists an L element of R such that for each epsilon greater than 0, there exists a K element of natural numbers such that for all n bigger than or equal to K, the absolute value of x of n minus L is less than epsilon. In this case, L is called.
How is your voice recorded?
It's recorded through the initial setup here of Logitech webcam. So it's recorded here. We have speakers, and that's you're not bothering us. It's okay.
Oh, I see them. I see one.
But it's through the initial software.
Thank you.
Thank you. In this case, L is called the limit of the sequence. And I probably had said that L was the limit. I know I've written down this definition now several times and we've used it. But L is the limit, okay? What I want to look at next is a theorem And this theorem says the following. So theorem is a big, fancy mathematical word. It just means big fact. Okay? So theorem, here's what it is. It's that a sequence of real numbers can have at most one limit. What this means is if you're looking at a convergent sequence, the limits are unique. So this is often the way we categorize this theorem. And when I say limits, we're talking about limits for sequences. We want to prove this. The way we're going to prove it, Chuck, is we're going to do it by contradiction. So I'm going to indicate to the reader that it's by contradiction. So here's what I'm going to say. Suppose x of n is a sequence. And what we're trying to show, our theorem says that it can have at most one limit. Okay? But if we suppose the opposite of that, the opposite of having at most one limit is having two or more. That's right. At least two. Two limits. Okay? And when we say two, at least two, that means that there are at least two distinct limits. So x of n has two limits, say L1 and L2, with L1 being different than L2. So it's got at least two, so it's got L1 and L2. Those are two of them, at least two limits. And they're not the same. If they're not the same, if they're not equal to each other, then one of them had to be, they're not the same. Then one of them has to be, they have to, have to be different from each other, but what does that mean? One of them has to be greater than another. So here, I'm going to write up a phrase that occasionally will occur in proofs. One of these numbers is bigger than the other. And so it doesn't matter which one's bigger than the other. Okay, one is bigger than the other. So we'll say this phrase, we'll say, without loss of generality, assume L1 is less than L2. It doesn't matter. One of them smaller than the other, one of them bigger than the other. We're just going to say L2 is the bigger one. Okay? Whichever one's bigger, we're going to designate it as L2. Okay. Look, we're trying to get a contradiction here. And we're saying, well, what if the sequence has at least two limits, L1 and L2? One of them's, they're different, so one of them's smaller than the other. Well, remember what it means for a sequence to converge to L1, sequence to converge to L2. What that means is after some point, all the terms of the sequence are really close to L1. And after some point, all the terms of the sequence are really close to the other one, L2. Is that okay? But close to, what we'd like to do is form some kind of region about L1 and L2 that don't overlap. So the idea I'm going to write here, you don't have to include this, but I'm going to write it right here, is that, look, here's L1, here's L2. What kind of region can I put about each one of them? The region is going to have to do with the epsilon we picked, so that there's no overlapping. So here, let's see, maybe I'd like to pick half the distance between what?
L1 and L2.
All right, between L1 and L2. Okay. So here's what I'm thinking. That's what I've got in mind. So that distance is going to be epsilon. So what I'm going to do is I'm going to consider, remember, our definition for convergence has to do for any positive epsilon. So I'm going to note, first of all, that L2 minus L1 is greater than 0. That comes from the definition of greater than. See, if L2 is bigger than L1, then their difference, bigger minus smaller, is positive. So that means it's greater than 0. So that says that L2 minus L1 over 2 is going to be greater than 0. And I'm going to consider this whole fraction here to be like my epsilon. So since the sequence x of n converges to, let's start off with L1, then what does that mean by definition? There's a spot in the sequence, K, okay, such that from that spot on, all the terms of the sequence are within this distance of L1. And there exists a spot. My spot I'm going to call K sub 1. It's a natural number, such that for all n bigger than or equal to K, the absolute value of x of n minus L sub 1 will be less than L2 minus L1 over 2. That's my epsilon. Yes.
When you said for all n greater than or equal to k.
I should say K sub 1. Right. Thank you very much. Okay, that's right. So what does this mean? What I'm going to do is that the first thing that I wrote up today had to do with how to translate an inequality involving absolute values as a compound inequality not involving absolute values. And that's what I'm going to use here. So look, I've got something inside absolute values less than a positive number. That means whatever was inside absolute values, that's xn minus L, is going to be less than that positive number, which is L sub 2 minus L sub 1 over 2. But yet that's going to be greater than negative that positive number. The negative version of that positive number. Brad, you know what I'm talking about, right? That theorem. So here, what's the negative of this, Brad? It will be L sub 1 minus over 2. So that's what I have. I don't have it all the time. When do I have it? I have it for all n bigger than or equal to k sub 1. I don't have it for all the x of n's. I just have it for the x of n's where n is greater than or equal to k. Now, if I solve for x of n, how am I going to solve for x of n? I'm going to add L. Well, wait a minute, I made a mistake here. It's not L, it's L sub 1. Okay, so I'm going to solve for x of n. How am I going to solve for x of n? I'm going to add L sub 1 to both sides. Well, really, I got to get a common denominator here, which is 2. So this, when I add L sub 1, it's the same thing as adding 2L sub 1 over 2. So here, when I add 2L sub 1 over 2 to L sub 1 over 2 minus L sub 2, what I'm going to get is 3L sub 1 minus L sub 2 over 2 is less than x of n, which is less than, here when I add 2L sub 1s over 2, I'm going to get L sub 2 plus L sub 1 over 2. And that's true for all n bigger than or equal to k sub 1. So that's a statement I can get based on the sequence converging to L sub 1. But we're also assuming that the sequence converges to L sub 2. So since, or similarly, since the limit as n goes to infinity of x of n equals to L sub 2, there exists another spot, let's call k sub 2, that's a natural number, such that for all n greater than or equal to k sub 2, the absolute value of x sub n minus L sub 2 will be less than that same epsilon we had before, which was epsilon 2, L sub 2 minus L sub 1 over 2. Thus, for all n greater than or equal to k sub 2, rewriting that inequality right here as a compound inequality without absolute values, what we have is L sub 1 minus L sub 2 over 2 will be less than x sub n minus L sub 2, which is less than L sub 2 minus L sub 1 over 2. We'll work with that just a little bit more. Before I leave, that board, I want you to pay close attention to this spot where we solve for x sub n in this case, okay? Using the fact that x sub n is converged to L sub 1. We're going to get something similarly for the same type of situation where we're assuming that x sub n converges to L sub 2. So remember that spot still on the board? I'm going to refer back to it in just a few seconds. Right, a summary, really, kind of these analogous statements. So here, based on what I said for L sub 2, we solve for x sub n for all n greater than or equal to k sub 2. We have, remember, I'm going to solve for x sub n, so I'm going to add L sub 2 to both sides. And what I did is L sub 1. Now remember, when you add, you got to get a common denominator. So it's 2 L sub 2 over 2 is what I'm adding. This will be plus L sub 2 over 2 less than x sub n, which is less than, here this will be 3 L sub 2 minus L sub 1 over 2. Is that okay with everybody? That's what we have. And so that's kind of the other analogous statement. I'm going to put a little double star. And I'm going to circle part of it just for a second, this part. And I'm going to go back and circle an analogous part of the other starred statement. That's here. So look at this. This says that x sub n has to be less than L sub 2 plus L sub 1 over 2. But over here, we have that same number, L sub 2 plus L sub 1, is less than x sub n. Right here. So x sub n is bigger than this number, but over there it's less than this number. That can't happen. Except our statements for what we're comparing is not the same statements. One of them is for all n bigger than k sub 1, and one of them is for all n bigger than k sub 2. So what I want to do is I want to pick one particular k such that both statements hold true. Now listen, this is the way I think about it. Look, statement 1 holds true when you get up to k sub 1. From k sub 1 on, the statement is true. Statement 2 holds true for, let's say, k sub 2 here and forward. If you want both of them to hold true, they hold true forward, from one spot on, then you better make sure for both of them to hold true, you better make sure that you're looking at n's bigger than the what between k sub 1 and k sub 2.
Epsilon.
No, not epsilon. So here, let me write on this sideboard. Well, I'm going to write it down for you in just a second, but just to kind of help maybe to get you to think about it. If I said, hey, from the case of 1, let's say that was 5. From the 5th spot on, we get what we want. And if I said, oh, really, from case of 2 equal to 11, we get what we want. The other thing we want, okay? If I want to get both things to occur, I better be bigger than 11. Is that okay? But when you're bigger than 11, you get both. Is that okay? And so, in general, I don't know, case of 2 is 11 and case of 1 is 5. In general, the way we make this happen in proofs is we say let k be equal to the maximum of those numbers. We go to the max. Okay. The maximum between the two numbers of case of 1 and case of 2. And when we go that far, for all n bigger than or equal to k, if you're bigger than or equal to k, you're bigger than or equal to case of 1. Okay? And so we have that initial star statement. That is 3 L sub 1 minus L sub 2 over 2 is less than x sub n, which is less than L sub 1 minus L sub 2 minus L sub 1 over 2. And we also have this secondary statement, because if you're bigger than k, you're bigger than or equal to k sub 2. And so we get this second statement, that L sub 1 plus L sub 2 over 2 is less than x sub n, which is less than 3 L sub 2 minus L sub 1 over 2. So this statement is a statement about all n's bigger than or equal to k, and they contradict each other. Okay? Here, I think I've made them. No, I wrote down the right thing. Except this one right here should be L sub 1 plus L sub 2. I miswrote it. Okay? It's L sub 1 plus L sub 2. That's what's written right here. I just didn't. My eyesight's not very good. So it should be plus. So here, when I have this and compare it to this, it's a contradiction, which yields a contradiction. So we didn't make a mistake in our logic. We didn't make a mistake in our calculations. What we made a mistake with is the assumption that we made. So what did we assume? We assumed that there was more than one limit. So that's wrong. Let me write that up. So our assumption that there are more than one limits more than one limit is false. So there can be at most one limit. And that's what we were trying to prove. So that is it. Make sure everything seems okay to you guys. If you have questions, you let me know. I'll give you a chance to ask about it. Does anybody want to ask anything? Maybe I erased what you wanted to ask about. Anybody wanted to ask about anything? You know, as I leave a little space here, pictorially, here's what we had. Here was x sub 1, here was x sub 2. What did we look at? We took the distance between the two. That's this distance, okay, whatever that is. You divide it by 2. That means you can go in this direction up to the halfway point, the midpoint. Is that okay? And back this far. And then you have this other region, halfway point, and then forward here. And what's being said is, by our definition of convergence, is that after some point, we call it case of 1, all the terms of the sequence after case of 1 had to be in here. And after some point, case of 2, all the terms of the sequence had to be in here. But they couldn't be in both here and here. Does that make sense after some point? That's the idea. Is that okay? That's why we can have at most one limit. Okay. Anybody have a question about what I've done? It's okay? All right. Well, let me move on then to another statement. And I'll write it up on this side and we'll try to prove it. It's a statement that says the following characteristics are equivalent. So here's what it says. It says, let x of n be a sequence of real numbers and let x be an element of R. Then the following statements are equivalent. So the first statement is x of n converges to x. B, the next statement is for every, or I'll say it this way, for each, that's why I like to say that, for each epsilon greater than 0, there exists a k element of natural numbers such that for all n bigger than or equal to k, x of n minus x will be less than epsilon. So those two statements are equivalent, but there's more that are equivalent.
Is that just the definition?
It sure is. Yes, that's going to be our proof. From the definition, from A we get to B. Yes. That is correct. Part C is also involved in this equivalency, is that for each epsilon greater than 0, there exists a k element of the natural numbers such that for all n bigger than or equal to k, the terms x of n satisfy they satisfy this. It's for part C. They satisfy that minus x plus epsilon, that's not what they write. I'm sorry. It's x minus epsilon. Yeah, that's right. Is less than x of n is less than x plus epsilon. In part D, it says for every neighborhood, so I'll say it this way, for each neighborhood, for each epsilon neighborhood, that's what we write. For each epsilon neighborhood, we call it b sub epsilon of x. So of x, there exists a k element of natural numbers such that for all n bigger than or equal to k, x of n is an element, so belongs to b sub epsilon of x. We'll give you about a second to write those down. Okay, so as you finish writing those down, let me say, what we're looking to do is to show that from one of these statements you can get to any other statement. So from A you can get to B. From A you could get to D. From D you could get to C. So one of the statements implies the other. Each one of the statements implies the other. And the way that we can show this, and the way we kind of standardly show equivalence between more than two things, is that we show a loop of implication. Starting with the first one, we show it implies the second one, which the second one implies the third, and the third implies the fourth, and then the fourth implies the first. That's what we're going to do. So A implies D is what we're going to show. B implies C. If you got C, you can get D, and if you have D, you can get back to A. And so from any one, you can get to any other statement. So here's the proof. We're going to let x sub n be a series. And we're going to let x be an element of R. The first thing we want to do is we want to show A implies B. So the way that we'll do this is we will suppose x sub n converges to x for this part. And then by definition, we get exactly B, as John pointed out. Since the limit as n goes to infinity of x sub n equals to x, by definition, for each epsilon greater than 0, there exists a k element of natural numbers such that for all n bigger than or equal to k, the absolute value of x sub n minus x will be less than epsilon, and that is B. So I've proven part of what I need to show. A implies B. Now what am I going to show? I'm going to show B implies C. That's what we're going to work on next. Listen, you know, it's kind of hard to keep up with these things, so I'm going to tell you what each one is. So what does B say? B says the following. Suppose, that's what we're going to assume, for each epsilon greater than 0, there exists a natural number, we're calling it k, such that for all n greater than or equal to k, the terms x sub n minus x will be less than epsilon. What we want to show is that for each epsilon greater than 0, there exists a k, such that for all n greater than or equal to k, that x minus epsilon is less than x sub n, which is less than x plus epsilon. So here, I'm going to let epsilon be greater than 0 be given. By assumption, there exists a k element of natural number such that for all n bigger than or equal to k, we have exactly what's written above. That is, x sub n minus x is less than epsilon. And now, let me give everybody a second. I'm very disappointed in my preparation for this class today. You know, not only don't I have the homework graded, but I didn't bring a Mountain Dew. And so I'm really not happy with myself. Not that I can't go an hour without drinking. I'm just giving everybody a second. Okay, look. Brad, Melissa, what was the statement I've been harping on today? It had to do with an absolute value inequality and rewriting it as without having absolute value. So here, Brad, if I have the absolute value of x sub n minus x is less than epsilon, how can I rewrite that as a statement that doesn't involve absolute value?
Negative epsilon
Yes, sir.
less than x sub n minus x, which is less than epsilon.
Right. And let me get some more room here. we're very close to having what we want. So for all n bigger than or equal to k, if we solve for x of n, what we'll have is, we add x to both sides from that previous inequality. We have x minus epsilon is less than x of n, which is less than x plus epsilon. And that is c. Okay, so we've done that part. So we've done A implies B and B implies C. Now we need to show that C implies D. That's what I'm working on. So here we suppose for each epsilon greater than 0, there exists a k element of natural numbers such that for all n bigger than or equal to k, x minus epsilon is less than x of n is less than x plus epsilon. What we want to do is show that for each epsilon neighborhood about x, there's some natural number k such that from that spot on in the sequence, so for all n bigger than or equal to k, x of n will be in that neighborhood. So I'm going to say let epsilon be greater than 0 be given. Okay. We need a k element of natural numbers such that for all n bigger than or equal to k, x of n is an element of v sub epsilon of x. That's what we want to have. What does it mean for x of n to be in this epsilon neighborhood about x? It means its distance from x is less than epsilon. That's right. Well, here's what I can say. So we've been given epsilon by assumption of c. There does exist a k element of natural number such that for all n bigger than or equal to k, x of n, I'm sorry, I didn't write it correctly, x minus epsilon is less than x of n, which is less than x plus epsilon. Melissa? You know, that theorem we've used 3 or 4 times now, relating an inequality without absolute values to an inequality with absolute values, can come into play here almost. So here's what I'll say. So for all n bigger than or equal to k, I'll have minus epsilon is less than x of n minus x, which is less than epsilon. Now I can use that statement directly. This is minus epsilon. So, rewriting that last statement as an absolute value statement. So for all n bigger than or equal to k, what do we have? We have the absolute value of x of n minus x is going to be less than epsilon. Okay. What is that saying? It says for all terms of the sequence beyond this point k, a and beyond, their distance from x is less than epsilon. So here's what I'll write. So, for all n bigger than or equal to k, x of n is an element of the set of what? The set of all real numbers, y, such that the absolute value of y minus x is less than epsilon. Okay, what am I talking about this? This set is the set of all numbers whose distance from x is less than epsilon. But what did we say about all the x of n's where n's bigger than or equal to k? Their distance from x is less than epsilon. So x sub n's are like these y, or one of these y's. Is that okay? Because their distance from x is less than epsilon. So, for all n bigger than or equal to k, x sub n, but what is the set? This is the set v sub epsilon of x. It's that neighborhood. And that's what we're wanting to show. Oops. So that was the C implies D. What do I need to do lastly?
D implies A.
D implies A. That closes the loop. From A we can get to B. From B we can get to C. From C we can get to D. If we can get from D to A, we can get from any one of them to any other one of them. Okay, so we want to show D implies A. So here we suppose that for each epsilon neighborhood of x, we call it v sub epsilon of x, there exists a k on the natural numbers such that for all n bigger than or equal to k, x sub n will be an element of v sub epsilon of x. That's what we're assuming. That's part D. What do we want to show? What was A? We want to show that the sequence x sub n converges to x. That's what I want to show. Okay, how am I going to show that x sub n converges to x? Well, really I'm going to do that using the definition. So if I wanted to prove that x sub n converges to x, what I do is I'd start off the same way we always start off. What is that same way we always start off when we want to prove that a sequence converges to a limit x? That's exactly what we say. What do we need? What are we looking for? We need this is all the same type of setup. What do we need? We need a, that's right. We need a k. Where is k?
In the natural numbers.
That's right. That's right, John. It's in the natural numbers, such that for all n bigger than or equal to k, the absolute value of x sub n minus x will be less than epsilon. I'm looking for that k. Well, we've been given this epsilon. By assumption, there exists a k, element of the natural numbers, such that for all n bigger than or equal to k, what do we have? We have that x sub n is of the epsilon neighborhood about x. So we're just going to expand, Mary, what the epsilon neighborhood is. So for all n bigger than or equal to k, x sub n is an element. What is this? It's the set of all y's. I've written it one time. It's the set of all real numbers such that the absolute value of y minus x is less than epsilon. That's right. That's what it is. So x sub n is one of these. It has this property. It's a number such that its distance from x is less than epsilon. So for all n bigger than or equal to k, x sub n has this property that its distance from x is less than epsilon. Therefore, x sub n is a sequence converges to x. And that finishes the proof of showing that these things are equivalent. So we showed A implies B, B implies C, C implies D, and D implies A. So from any one of the statements you get to the other. If one of them is true, all of the statements involved are true. If one of them is false, all the statements are false. The next thing, or essentially the last thing I want to do, is I want to talk about something called the tail of a sequence. The M tail of a sequence. So here's a definition. It says, given a sequence x of n and a natural number m, the m-tailed sequence, that's what I'm defining, m-tailed sequence of x of n is the sequence x sub m plus n, where n runs from 1 to infinity. Oh, what the heck does that mean? Let's give an example so we make sure we understand it. I'm going to look at one of the more famous examples of a sequence that we've been looking at. 1 over n. Consider the sequence x of n as n runs from 1 to infinity equal to the sequence 1 over n as n runs from 1 to infinity, which is equal to 1, 2, 3, 4, 5, 6, 7, goes on forever like this. All right, I'm sorry that I'm not getting them all right on the same board here, but we can have it.
I think you mean 1 over.
Yeah, oh gosh, this is wrong. Wow, what happened to me? This is 1 over 1. This is 1 over 2. Yes, sir. Thank you very much. 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7. It continues on like this forever. Gosh, that's terrible. If I'd had my Mountain Dew, I'd have been okay. That's right, you're right. So I'm going to talk about what is the fourth tail sequence. I didn't put this on the board, did I? I think I didn't. I think I made a mistake. I don't think I did this. So look, I'm defining the m-tail sequence, what it is. If you give me a sequence and a natural number m, the m-tail sequence of x of n is the sequence x of m plus n as n runs from 1 to n. We'll do an example. We're going to consider x of n to be 1 over n, which is n runs from 1 to infinity, which is this sequence here. And I want to find the fourth tail sequence. That's what I'm going to write. Sorry. Okay. So the fourth tail sequence, this is the last thing we get. What is it? By definition, it's x sub m plus n, and n runs from 1 to infinity. Except m is the mth tail sequence. So here, what's m? Say it again, Chuck. 4. 4. Okay? So here's the way that I think of this. Over here to the side, remember what x of n was? For our sequence, what's x of n?
1 over n.
1 over n. So the index here matches what's underneath 1. So here our index is 4 plus n. So what we're going to have is, this is really 1 over 4 plus n as n runs from 1 to infinity. And what that's equal to is the set when n is 1, we get 1/5, 1/6, 1/7, 1/8, and so forth. So the fourth tail sequence is really the entire sequence except the first 4 numbers of the original sequence. Is that okay? So we've kind of cut off some of the sequence and just looking at the tail end of it. What's tail end from some point on. Is that okay? That's all we're saying. Now the next thing we're done. Now the next thing we're going to say is that when you talk about convergence, and that's the main thing here for sequences, when you talk about convergence of sequences, remember what we have is this certain point, if you converge, a certain point, K, you get really close to L. From there on, you're really close to L. So it doesn't matter what happens in the first K of the terms of the sequence. Just after some point, you're really close to L. You can bounce wildly everywhere. And so really, if you converge, your M tail, whatever M is, has got to converge to that same number. Is that okay? So it just matters. Convergence, really, and what we're studying here, is to emphasize it doesn't matter what happens in the beginning. It's at the end that we're interested in for convergence. Thank you very much for your time.